Okay, good morning. Let's get started. So just some of you have pointed out to me, and I know that too, that the topic that we are talking this week and next is not in your book. Okay, so of course there are other books, but typically they cover this subject at a much deeper level. They go and talk about all design of digital circuits and so on, then to ultimately get to the two questions that we want to answer today and then also probably Monday. Those are those questions are how fast the circuit can go first, and that then sets the platform for us to understand the trade-off between power, speed, and complexity. And that's incredibly important. Understanding these trade-offs is critical if you want to start a company or so, do something new. You need to position that right. You need to look at these power or energy trade-offs and speed trade-offs. There is no room anymore almost to make something new if you cannot somehow control the energy. Most innovations today in circuits, like what's the next generation cell phone? It's had battery life, or alternatively, it has the same battery life, but it does more things. So power dissipation per function has been reduced. And we need to understand why that is, what the opportunities are, and that's what we talk about here. I cannot find this in any textbook that doesn't take an entire semester to go over until we can answer this question. So let's ask ourselves this question. How fast can a digital circuit go? Well, in fact, that's linked, of course, to power dissipation. If a circuit could go infinitely fast for any algorithm that terminates in finite time, that algorithm, of course, then would take zero time, and therefore we would need very little energy, right? Well, how fast can this thing go? How would we go and try to answer this question? Well, let's think about what's actually happening. This is actually a circuit that I totally made up. It presumably does nothing useful, right? But what's happening is the inputs of this circuit, when the circuit is supposed to do a computation, the inputs, they change, right? And then at some later time, in this case it's an inverter, at some later time, the output of the inverter is also going to change. But it does take some time, in particular if you were to draw this like on a scale like this, right? Then the input may be doing this, and then the output will be doing something like this, right? The output gradually increases. It does take a finite amount of time, and this time here, that's the delay. Now, obviously the circuit cannot do the next computation before before the previous computation has completed, right? Okay? And so basically TD tells us the fastest rate at which we can do computations one after the other. Okay? So even though digital circuits are very complicated things, even much more complicated than what I sort of sketched here, if we can understand what the delay is from one gate to the next, for the information to go from one gate to the next, we can predict for an entire very complicated circuit how fast it can go. So fortunately, we have to answer only a very, very simple question, relatively, and that is, what is the delay going through one gate? Okay? So that's what we're going to do now. Okay, so it's basically the same thing. Secondly, actually, we are here, for simplicity, we are just going to use inverters as the model. So we say there is a first inverter, and the input to that inverter changes. And then we want to know how fast the input to the other inverter changes. Okay? I suggest that you try to stay awake. Maybe you can take notes that will help you to stay awake. But it will be this is interesting material and very useful stuff to understand. Okay, so So again, actually in the timing diagram, I said that already. For example, the input here, V1, may be going from high to low. That means it goes from usually VDD to VSSS, which of course usually is 0 volts, right? Okay, and then the output of the circuit, that's V2, is gonna, if it's an inverter, it's initially low, right? Because the input is high, then the output is low, and then the output of that V2 is going to gradually increase like this. And well, how do we measure the delay? Well, we go and look at 50% of VDD. Okay, so we go halfway, and we look at this here. This is what we call the delay. Okay. At 50%. Okay? And it turns out that that's just the right number to use because the next gate then also has the 50%, sort of we split the delays nicely, yes.
And the 50% is sort of kind of arbitrary?
No, it's not arbitrary because of this thing that then we split, then when we cascade multiple gates, we add up correctly, we get the correct, if we can calculate the 50% delay of each gate, cascade n of them, and we simply add up all their individual delays. And we get the right number if we use this 50%. Okay?
So a gate starts to switch when its input's halfway to...
Yeah, that actually is not completely true in practice. It will start somewhere in between, and it will switch slowly first, and then faster, and then slow again, and so on. The exact process is complicated. Turns out, in order to estimate the overall delay, we don't need to look into the details of this transition. If you're interested in that, then take 105 and then afterwards 141. And in 141, you go through this at a much more detailed level. Here, we are trying to go to the big conclusions. We want to understand on a large scale how the performance and energy consumption of digital circuits vary. Okay, so that's why we use here a very simple model. That's on purpose. Some of you will find them just hard enough and confusing enough, but the simplest model that we can get by with. Okay, so some of the details, they're oversimplified, but the results are exactly on the mark. They're correct. Okay. So now, in order to calculate the delay, of course, we need to understand what's going on inside that inverter. And so this is a quick review of what we did in the last couple of lectures. So we have an inverter, the symbol, and then we've seen that we can realize that inverter with switches. So that's in the middle. And then, of course, we can use transistors, and that's what we do in practice, to realize these switches. The reason we can do that, the fact that we can do that is the reason why digital circuits are interesting. If there weren't transistors and they weren't terribly inexpensive and we couldn't make billions of them, nobody would talk about digital circuits. Couldn't make them. So this whole field wouldn't exist. We wouldn't have this class today. Okay, so we can do that. And now here again, there is on the left side the inverter. Now it's exactly the same thing as the little triangle with the bubble, but it has two transistors to implement it. That's a more detailed view. And now we go and make the equivalent circuit model, right? So what is this PMOS transistor? Well, if you go back a couple of lectures, or actually one lecture, then you see the PMOS transistor, or any transistor for that matter. At its input, it looks like a capacitor, okay? And its output, it looks like a switch. But it's not an ideal switch. And there are lots, once again, there are lots of non-idealities when we look at transistors. And you can do entire PhDs just what's going on in a transistor. Okay? If we do that, then maybe if we want to get a PhD or so, that's the right thing. But if we do that consistently, we'll get nowhere, right? So as engineers, we always use a model that is as simple as possible. Possible meaning it still gives us the right answer, but not any simpler. So that's what we do here also. So the transistor isn't an ideal switch, and the non-ideality that we want to capture here is that when it's on, it should be a short circuit. Well, in our model, when it's on, it has a finite resistance or on. Okay? So there are two transistors here. One, it's called PMOS. That's not very important. They have names, right? And the other one's called NMOS. And that's the one here. And both of them, they really look like capacitors on their input, and they look like switches with some finite on resistance on their output. And the difference between NMOS and PMOS is that the switch turns on for input voltage high for the NMOS or low for the PMOS. Okay? Yes?
So the delay, is it caused by the fact that there's a RC delay of this? No?
Perfect. Thanks. Of course. So now, now we have to go. Now that we understand what's inside that inverter, your colleague already mentioned. Well, gee, there got to be an RC thing in it. Well, yes. So now, in order to figure that out, we cannot just have one inverter. That's over here, but we need to put two inverters in series. Why? Well, because the first inverter has this finite output resistance, or on, and the second inverter provides the C in our RC circuit. So what we really do is we take two of these guys and we put them in series, right? We just connect them together. But now I did one more thing here. What did I do in addition? Well, I got rid, for example. So let me first of all, over here to the left side is the first inverter. On the right side is the second inverter. Let's discuss the first inverter first. That inverter, its input voltage is first high, and then it drops to zero, low. Okay? So when the input voltage is high, well, then the output of that guy is going to be zero, right? So initially, this voltage, that's the output of the first inverter here. Initially, this is zero, okay? And then just at the moment where the input to the inverter switches, so now its input is zero, at that moment, this switch here turns off, and this switch here turns on. Okay? Well, if the switch is off, I can get rid of it. And I, of course, can get rid of this also. That's why there's nothing here. I did redraw this thing. Again, it's almost a mantra that I tell you. Do that when you analyze a circuit. If a switch is open, all the stuff that's connected to it and the switch, they're totally irrelevant. But they still serve to confuse you mightily. So redraw the thing and get rid of them. Okay? So that's what I've done here. Okay? Then on the other hand, this switch here is on. Well, the switch is a short circuit. But the on resistor, of course, is still there. So that's what I put there. An on resistor is a short circuit. Okay? So that's what the first inverter really looks like. The second inverter has a bunch of capacitors, this one and this one. And then, of course, it has its own switches and so on. But because we only want to know the delay from this input to this output, it doesn't matter what else is there, right? Doesn't matter that other stuff is hanging over there. Doesn't affect. There is no current flowing directly into the input of a switch. There is no current flowing, right? Here, this current here is zero. Okay, so I can get rid of all of the stuff. So that's really the model that I have here. So I simplified the model a little bit further, and that's what I got here over here now. How did I simplify it further? Well, I realized that this stuff here doesn't matter either really anymore. That's the whatever previous gate comes in front. It needs to drive this capacitance. It needs to supply the charge and current, whatever, in order to charge or discharge these capacitors CG. But that delay belongs to the previous gate, and we don't have to add it into this one, right? So we just assume that the previous gate switches. Once the previous gate has switched, we say, okay, now the clock's ticking. How long does it take for this one to switch? Okay? So now I have a really simple model. There is just a resistor that pulls these capacitors, that pulls this node, the output Y here, pulls that one up. It starts at 0, and then it increases. Right? Actually, that's shown down here even. It starts at 0, it increases exponentially because the capacitors are being charged through this resistor R1. Now you've reduced this to a circuit that, of course, you are familiar with. You've solved these circuits before. Okay? So I've written here the solution, right? I wrote the differential equation. I realized, well, dV dt is 0. Why is it 0? Yeah, the supply voltage is supposed to be a constant, right? Actually, it's not always, but supposed to be constant. So I used that. That helped me simplify that. Then we know how to solve first-order differential equations. I did that. I write it down here for you. And then I said, well, the voltage at the time, TD, is how much? Well, it's 50% of VDD. 50% of VDD. And then, of course, it follows this equation I got from there. Solved, and then I find that the time delay is tau times logarithm of 2. Well, you know what logarithm of 2 is. What in the world is tau? That's the RC. Actually, we have to look very carefully at our equation. What exactly is it? Tau is actually 2 R1 times CG. Okay? Okay? That's for this circuit. In the homework, you have a couple of other ones. The procedure is exactly the same. But of course, the tau for those is sometimes going to be a little bit different because the circuits are a little bit different, right? Okay? So you have to go through this again. This is not something to learn by heart. What you should learn is how to do this analysis, okay? Because it's different for every gate. What are these CG and R1? Where do they come from? That's the transistor, right? If you make the transistor very long, what happens? R1 goes up and CG goes up. If you make it wide, well then CG goes up, but R1 goes down, and so on. Okay? If you have a better technology, then these numbers are going to be smaller. This product's going to be smaller. That means that our circuit can go faster. Okay? So in fact, the typical values for R1 CGs or CG are in the tens of picoseconds to hundreds of picoseconds. Okay? All right. So again, this analysis, it's not terribly complicated. You just got to be systematic, right? I drew a number of transformations of the circuit, made them simpler and simpler, and then afterwards it's simple RC delay, a first-order equation. Here's another example. Again, for example, let's say that the input here switches, and then the output, what's going to do? What is it going to do? It's going to go low, right? And again, it's going to have a time constant. Well, now, if we look carefully at the analysis before, what's this guy going to contribute? It's a resistor, and the resistor is going to be connected to VDD or to ground. Well, it has two resistors inside, but when it is switching from high to low, is it the NMOS or the PMOS that is actually turned on?
The input is high, so the output should be low.
Yeah, so the switch, the resistor must be pulling low, okay, to VSS, right? That's the R on, of that first inverter. And then we have capacitors here. How many capacitors do we have here? Well, at the input of every inverter, we had how many capacitors? 0. No. How many capacitors are there? Well, we could go back. Well, I see one capacitor. I see a second capacitor. Makes perfect sense. There are two transistors in every inverter, and each transistor has a capacitance CG. Huh? Okay. So there are actually 2 CG for every inverter, and there are how many inverters? 5. So this is actually 10 CG. Okay? So the time constant now is R1 times 10 CG. Okay? Now, if this is puzzling for you, what are you going to do? Well, you can come to the office hours and ask, but if you don't want to do that, what can you do? If your life depended on, well, your life doesn't depend on stupid stuff like that. Or it's not stupid, it's somebody. But nevertheless. But no, if you wanted to analyze this and, this insight and so on, looking into these inverters without actually really popping them open is confusing, what are you going to do? You do exactly the same thing I did. Right? You go through this... You start here and you draw the equivalent circuit and so on. Okay? So actually this slide asks a question. Now suddenly, of course, if the time constant's 5 times longer, well, that thing is going to go slower. It's going to be 5 times slower. Is that a problem? It very well may be. That may be in the critical path somewhere, right? The microprocessor, everything else, the multiplier is done, the adder is done, and somewhere, some path isn't quite done yet because it takes more time. So then we would like to make this path faster. How would you make it faster? What? Syrup? Now, how could we make it faster? Well, yes.
Notice that those inverters are, each inverter goes directly into another inverter and take both out.
Okay, fine, that's a fair idea. Maybe we could get rid of some of the inverters, and could be sometimes it's possible, right? We haven't minimized our circuits correctly. But on the other hand, there is probably more stuff hanging over there. In fact, structures like this, trivial and useless that they look like, they are very often used to distribute the signal to many different places. And so actually there is a big capacitor hanging here. Why? Because there are lots of other gates over there, or there's a long wire that gets over halfway across the chip, right? So this circuit you find that all the time. And if you take EE 141, then you spend a week or so just optimizing the delays through inverter chains, maybe even more than a week. Okay, but we want to make this faster, so if we could get rid of some of the inverters, that of course would help. Well, so if that doesn't help, well, let's look at the equation. The equation has 10 CG in it. Can we reduce the CG? We cannot reduce the 10, right? Unless we remove the number of some of the inverters. So let's just assume that we are not happy with that solution. Could we reduce CG? Well, how? What? Make it shorter. Exactly. We could reduce L. Now, it turns out that when we build inverters, we always use the minimum L that the fab tells us they can make it with. But of course, we could maybe have to pay more money or whatever. We could say, no, we are not using the 90 nanometer process. We use the 45 nanometer process, and then we can reduce L, make it half as long. That would be good. Yeah, what other ideas do you have? You went? Okay, so reducing CG is a good idea, except that we have to call up the fab. Can you do it? And then we have to change the technology. Very often, of course, we don't want to do that. Very often, even we can't, because even if you work at Intel, you work in the fastest technology that they currently have. There is no faster one. You would have to wait 3 years, right? Or 2 years or so. Yes? Okay. Could we put an op-amp? Well, could we put some amplifier that's more powerful than that little inverter, right? That's really the thing. Yes, actually, and in the homework there is such a solution. Turns out that you really wouldn't put an op-amp in there. An op-amp wouldn't be the right answer because op-amps are very precise circuits, and for being precise, they go slow. If you think about it, in digital circuits, you really don't need precision. High and low, I mean VDD and VSS, even if it's not quite VDD or not quite VSS, somewhere a little bit in the, if it's not smack in the middle, it's good enough, right? In an analog circuit, that's not good enough, right? In an analog circuit, if you just, the voltage is a little bit higher or a little bit low, your strain sensor, your balance wouldn't work at all, of course. So op-amps would not be the right answer here. But you could put some other amplifier, probably a more powerful inverter there. Actually, now I gave the answer. I think you wanted to say something? Okay. Yeah, if we... So you...
branch the initial input into 2 inverters and then branch those into the 5?
Exactly. That's perfect. Thanks. That's the solution. Why not take 2 inverters? Now what happens? What happens to this term here? Does it change? No, it doesn't change. I mean, we still have 5 inverters hanging there. They have 10 CG load. It doesn't change at all. What about this guy? Yeah, there are now 2 resistors in parallel, right? There are 2 resistors in parallel. So 2 resistors in parallel, well, they have half the resistance. So this one goes into half, and now it go only 2.5 times slower than if you had a single inverter hanging there. If you wanted to go at the same speed, well, you simply would have to put 5 inverters here. Now, I'm not going to draw 5 inverters. I'm going to do what everybody else does also. I just write M equals 5 next to that inverter. And it's shorthand for saying either you use 5 inverters, you put them in parallel, or you make the transistors in these inverters 5 times wider. Can do either. Depends on the process of and your preferences. Okay? So that's how we do that. Well, if you can't reduce CG, reduce R1. Okay? Yes.
But what about the node just before it?
Yes. It's a very, very good point. There is an example in the homework that illustrates that a little bit. In that example in the homework, it's a cascade of such inverters, exactly the same problem, right? That I make this transition faster, but what about the transition before? And if you go through that homework, what you will find out is that playing games like this, they slow down the circuit a little bit, but a lot less than if you didn't do this, if you didn't scale up. If you had M always 1 everywhere, then it would get a lot slower than if you, okay, so maybe then the whole thing gets a little bit slower, but not like 5 times slower, right? Yeah.
In the previous slide, with the circuit diagram, like the passive, or one more back, why can you ignore the resistor on the other? Like initially, if Vy is 0, at least one of the capacitors on the right is connected to a resistor, right?
No. It's not connected to a resistor here. It's connected to a switch, right?
Well, one of the switches is closed at any given time, right? They can't both be open.
That's right. Over here, but that's the delay going forward. That's the next delay, right?
Right, but when we solve your differential equation, aren't we
Yeah.
having current going in one direction? Like there's a branch to VSS or VDD depending on
There is these capacitors here. They belong to the previous guy, right? These the switches and resistors and capacitors over here, they belong to the next guy. We only need to look at this resistor and then the capacitor that loads it. The next connected over here, all we connect to is switches. They don't draw any current. Okay? Yeah. Okay, so those are all good questions. Yeah, we can play around with this stuff now, right? We can make it fast and slow. And again, in the homework, there are some questions that allow you to think about that. And you will see that you're totally right. If you have to drive 5 inverters, there is nothing but going slower. But you can go a lot slower or less slower if you do it cleverly. Okay? Any more questions? Okay, so now I told you that really the big question that we want, why we do this, is we really needed to get good enough an understanding of digital circuits so that we can answer this question. And it's literally true, right? Understanding these trade-offs allows you to make the business decisions to start in the right direction. Be sure that Intel, before it launches a new microprocessor design, also it analyzes this. Okay, and in fact, some of this I learned from researchers at Intel. So why do we care? Again, yes, I mean, you can come up with a new kind of portable phone or God knows what gizmo, and it can do 3D movies and God knows what, and wonderful, and you have to hold a car battery. Nobody's going to buy it, okay? It's extremely inflexible. If it dissipates more power, Apple will not even answer your phone. They are not interested because there is no way to sell it, okay? So we need to understand what we can do when we have a great new idea, what we can do to implement it in a form that it doesn't take more power, such as actually attractive. Okay, so now, now of course there are other more interesting or insightful questions. So first of all, is the question: why do digital circuits dissipate power in the first place? Anybody has an idea? Yeah. Okay. All right, sort of. It turns out that even if the resistors weren't there, we'd still have the same power dissipation. Yeah.
The capacitors.
Yeah, we have to charge and discharge the capacitors. And I'll say that in a little bit differently again on the next slide. So that's the question we'll have to answer. Another question is, could I save power by going more slowly? Notice that's not so obvious. If I go more slowly, maybe I don't draw as much power from the supply. On the other hand, to do a certain amount of computation, if I go more slowly, takes more time. So less current over longer time. Is it a win? Does it hurt me? Do I benefit? Right? It's not trivial. What's the answer? Well, we'll see. Okay, so we already had a 20,000-foot model of a digital circuit. And now we have an even simpler 20,000-foot model of a digital circuit. A digital circuit is basically a sea of capacitors. And these capacitors, they are connected through switches and resistors to either VDD or VSS. Okay? Each capacitor through a maze of switches, 1 or 2 or whatever, is going to be connected to either VDD or VSS. And what's happening Suppose that one of the switch, right, in practice, so there may be an inverter, right? One switch is open, the other one is closed. How much power is being dissipated? Come on. You look at that circuit and you determine, oh yeah, one switch is closed, the other one is open. How much power is dissipated? Yeah.
The power is being stored in the capacitor?
Yeah, exactly. Energy is stored in the capacitor, but there's no current flowing. Consequently, the power is zero. When nothing changes, the power is zero. It's a wonderful thing. If your computer just sits there and does nothing, in principle, it doesn't dissipate power. Again, something that is true only to first order. In practice, they leak a little bit and so on, and it's getting worse. So if we stick with that interpretation, then really, while it's not computing, it's not dissipating power. That's a very good thing. And that's actually the reason why CMOS is so popular. It used to be that we used other methods on how to make digital circuits, where they used power even when it was just sitting there, waiting for you to hit a key. Well, this doesn't do that. When you don't do anything with your computer, just sits there and it waits for you to ask it to do something, and then it needs power to do that. Well, why does it need power? Well, because these capacitors, let's say this guy was charged to VDD, and then afterwards, switch configuration changes, I discharge it to zero, the energy stored on capacitor goes away. Let's look at that. Okay, so we've already said that static power, what is that? When the circuit's not switching, when it's not doing anything, static power is zero. Okay? Right, so but now, suppose that there is a transition that this circuit here goes from low, the output here goes from low, V2 goes from low to high. Does it use any power from the supply? Any energy from the supply, I should say, for this transition? Yeah. Actually, I would like that. Figure that out, please. How much energy does it pull from the supply? Talk to your neighbors. Wake up. No, really. Go talk to your neighbors. Figure it out. How much power do I need from the supply if I want this terminal go from 0 volts to VDD? Here is 0 volts. Here is VDD. What is it? I go blazingly fast. If you don't bother answering this, I go blazingly fast afterwards. Yeah, I know. Many of you know already. I would like that the other ones think about that too. It's not hard. Can somebody in that group over there? It's an idea. Hey, the floor is not giving the answer. Yes. Is it 1/2 CV squared? Who is for 1/2 CV squared? Who is for something else? You're for something else?
I think it's 1/2 CV.
Okay, so that's 1/2 CV squared. Yes. What is it?
I get 2 CV squared just because the resistor doubles the energy and there are 2 capacitors being charged.
Okay,
Well, the next gate will have 2 capacitors in it.
okay, so let's call the capacitance, whatever it is there, let's call it C.
Okay.
Then what's the energy? CV squared. That's right. There are 2 in this room who believe that's the case. At least 2. Why is it? Why is VDD squared and not 1/2 VDD squared? What is the energy stored on? We actually went over that. What is the energy stored on the capacitor? How much? 1/2 CV squared, right? Or CVDD squared, right? Okay, so there we agree. The energy stored on this guy is 1/2 CVDD squared. Why is he then saying that the amount of energy we need from the supply is not that, but twice as much, namely CVDD squared without the 1/2? Why? We did that because no matter how you charge a capacitor, there is some resistance here, and while you charge the capacitor, you can make the resistor very big, very small or so. If you make it very small, then you can go fast, but in that resistor, you dissipate energy while you're charging the capacitor. We did calculate that a few weeks ago. That's why we did it. And the amount of that energy is, and now somebody else could remember, 1/2 CV squared. We are going to, half of the energy is going to be dissipated and the other half is ending up on the capacitor. So when we switch the output from the inverter from 0 to high, from VSS to VDD, the amount of energy that we consume from the supply is this amount, with half of it being then still available, stored on the capacitor, and the other half being dissipated in the resistor or switch or transistor or whatever you want. It doesn't matter what's there. It's always 1/2 CVDD squared. You can solve terribly nonlinear equations, and then the result is going to be, 1/2 CVDD squared. Okay, what happens if the output now goes from VDD to 0 volts? What happens then? Do we pull any power from the supply or any energy from the supply? Well, no, yeah. The supply is actually disconnected because this switch is open, right? But what happens to the energy that's stored on a capacitor? It's dissipated, right? So in a round trip, we use for one transition CVDD squared. For the other transition, we use 0 energy from the supply. So the round trip actually costs us 1/2 CVDD squared. That's the cost of a round trip. Whenever the gate switches from one state and then at some point later it switches to the original state again, then in that entire operation, it dissipated an average of 1/2 CVDD squared. There is a 1 and there is a 0, and the mean of 1 and 0 is 1/2. Okay, that's where the 1/2 comes from. It's a round trip. It's not just one operation. Okay. In reality, we paid nothing for one transition, and we paid twice as much for the other. Okay. So now, what's the power, right? We looked at the energy. What's the power? Well, every time our output changes, makes a round trip, we need CV squared, and we need CV squared. And so per transition, we need, actually I didn't say that right. Per transition, we need 1/2 CV squared. So the energy, the power is equal to energy times time. So that's energy over time, energy per time, right? So that's energy times the frequency at which this thing is going. Okay? If we go faster, of course, this thing is happening more often, and then we use the energy many more times. Okay, so that's going to be equal to 1/2 CVDD squared times Fs. And that's the average power because, again, on one transition we actually use nothing. from the supply, and on the other transition we use twice as much. Okay? All right, so now now that was just for one single gate. Well, one single gate isn't that interesting. The whole point of digital circuits is that you can use these trivial things called gates. And if you have enough of them, and enough, maybe a few 100,000 often, then you can do incredible stuff with them. So here is the equation from the slide before, but a little bit generalized. So we have our factor of 1/2, we know that one. Then what is this n? Well, n is the total number of gates that we have, right? In our digital system, we have not one, we have not two, so we have n, and n, again, very often thousands or hundreds of thousands. And then C in, that's the average capacitance, average input capacitance of every gate, okay? Of course, that is a little bit the question, what is that, and so on. But it turns out that if you look at digital design, you will find that, well, typically you have maybe 2 or 3 gates connected to one before, and so you can get a pretty good idea what that Cn is, maybe 6 Cg or something like that. Okay? This one's easy, that's the supply voltage, Fs. Well, that's the frequency at which the computer runs. So, for example, 2 gigahertz for a recent laptop or so. What's this eta? Well, your laptop, when it does when you tell it to do an addition, what is the multiplier doing? Come on, hey! The thing does an addition. What's the multiplier doing? Nothing, exactly. So not all of these things are doing something all the time. So eta, it's the percentage of the ones that are actually doing something. So that eta may be depending on what it is. In a general purpose processor, you have all this stuff there. There's a floating point unit, but gee, you do only financials. They don't need floating point. They only work with thousands or millions of dollars. That sits there, right? It's just there because, well, the guy could use it in order to run a SPICE simulation, maybe. Right? So in a general purpose processor, that eta is very small. And in a dedicated circuit where you put only there what's really needed, well, then eta is going to be larger. Okay, so why are we doing this? What do we want from this? Why do we write all of this stuff down? Exactly, we want to minimize. We want to minimize the amount of power. So how could we minimize the power? We cannot reduce 1/2, okay? So 1/2's out. N. What can we do about N? You what?
Simplify.
Exactly. We had these De Morgan's rules and so on. Every when it's synthesized or add, well, we came up with an incredibly long equation. Well, turned out that there were ways to reduce it. Okay, so of course we're going to do that. Okay. What about Cin? Could we reduce that? Yeah, again, we could use a more modern process. What would the more modern process do for us? Smaller L, exactly, reduce the channel lengths. Hey, if I cut the channel lengths in half, and then my capacitance, and leave everything else the same, not what I usually do when I scale process, but if I did that, then the capacitance would be cut in half, right? VDD, well, actually, let's skip VDD for a moment. FS, the clock speed. Minimize it, right? But again, of course, hey, you know, if you want to do video compression, you cannot just, or even if you want to run SPICE, you don't want to make the clock speed 1 hertz and wait until you retire before that thing finishes. So there is more to that. And ETA, well, yes, we can try to build the stuff. So it seems to be a good idea. When you don't need it, don't switch it. And so turn off your clocks. And lo and behold, if you go inside your microprocessor and look carefully, you'll see that there are switches to turn off the clock to the floating point unit when the floating point unit's not needed. Well, you don't want this ETA any bigger than it has to be. VDD. If we reduce VDD, obviously that's the big prize. Any ideas why don't we run with 1 millivolt?
The amount of precision to switch is greater. You don't have.
Probably not.
Circuit noise.
It's a concern, but there are probably ways to get around it. No, there is another reason. Our transistors don't work. Okay, transistors, they need a few hundred millivolts, otherwise they don't work right. A colleague of mine, Eli Jablonowicz, he just got a huge NSF center, $12 or $15 million or so, to try to come up with transistors that actually would allow us to go at a few millivolts. He doesn't know how yet. Well, I mean, if it was that trivial, you can be sure AMD, Intel, Freescale, and all of these guys, they would have done it already, right? So maybe you have an idea. Maybe you can join his research team in a couple of years or so. Anyway, so we will talk about that next time, and have a good weekend.